All right, guys, this is where we stopped off with 10.2 part 1. So we have this equation here, and it said to transform the polar equation to an equation in rectangular coordinates, then identify and graph the equation. All right, if I look at that, it looks somewhat familiar because now I have 10 cosine theta. So I'm looking at that, and I'm like, yeah, that looks kind of familiar to me. What can I do with this? Well, if you remember correctly, we said that x equals our cosine theta, right? And we also said that y equals our sine theta. But in this case, we're dealing with cosine. So what I'm going to do is I'm going to try to make this right-hand side, 10 cosine theta, look like r cosine theta. And to do that, I'm going to multiply both sides by r. So I'm going to multiply both sides by r. Geez, I don't know why that's doing that. And I'm going to put a little note that I did that. Multiply both by r. And when I do that, I get r squared equals, and I'm just going to move this around, 10 r cosine theta. Okay, at this point, what I can do is now substitute in for r cosine theta. And I know that's x. So I get r squared equals 10x. Okay, I'm going to bring this equation over here. So I'm going to put a little arrow that's going over this way. And remember that we also know that r squared is equivalent to x squared plus y squared. So that's the next thing I'm going to do. So I'm going to substitute in for r squared. So I get x squared plus y squared equals 10x. So once again, I sub in x squared plus y squared for r squared. Okay, at this point, I know it's a circle, and the reason why I know it's a circle is because both x and y are squared. However, I don't have it equaling just a value. You know, it's a value plus a variable. So we have 10x. So I know that this circle is not positioned at the origin, it's moved. So what I'm going to do, and hopefully you remember from the last section, is I'm going to complete the square. So I'm going to go ahead and bring the 10x over, and I'm going to go ahead and put the y squared on the other side. At this point, I want to complete the square. So to complete the square, I take half of the value of 10, which I get 5, and then I'm going to square it. And when I do that, 5 squared is 25. So I'm going to add that value to both sides of my equation. So x squared minus 10x plus 25 equals negative y squared plus 25. Okay? And the whole reason for completing the square is it's magical because it makes a perfect square trinomial that factors out into two binomial sets that are exactly the same. So I know this factors out into x minus 5 squared. And on this side, I have negative y squared plus 25. I'm going to bring the y squared over to the other side, so I'm going to rewrite this as x minus 5 quantity squared plus y squared equals 25. Now, I'm almost where I need to be, because if you remember the equation of a circle, and I'll put that over here, is x minus h squared plus y minus k squared equals r squared. So I almost have my equation where I want it. I'm just going to rewrite that 25 as 5 squared so it matches up. Now, I know a bit of information. I know my center of my circle, and it's going to be h comma k. In this case, I have an h of a value of 5, and k is 0. So my center is at 5, 0. And my radius is equal to 5. Now that I know this information, I'm able to graph this equation. So once again, what is this? This is an equation of a circle where the center is 5, 0 and the radius is 5. And that's why I had to complete the square, is to figure that information out. So I'm going to go ahead and change my rings. So I'm changing them in terms of 5. So the radius is now 5, 10, 15, 20. So do that first. And remember, my center point is at 5, 0, so that's right there. Okay, now remember the radius is 5 units, so I'm just putting dots to kind of guide my hand. but I'm going to draw a circle that has been moved. So the circle was moved off of the center, and now its center is 5, 0, and its radius is 5. So that is the graph of r equals 10 cosine theta. And in rectangular coordinates, it would be x minus 5 quantity squared plus y squared equals 5 squared. So let's see another one like this. Transform the polar equation to an equation in rectangular coordinates, then identify and graph the equation. So we have a similar situation. R equals 2 sine theta, and I know that y equals r sine theta. So what I'm going to do is go ahead and do the same thing I did for the last one. I'm going to multiply both sides by r. And when I do that, I get r times the r that was already there, and r times 2 sine theta. Okay, so this becomes r squared equals 2r sine theta, and now I'm ready to sub in. So I'm going to substitute in a y for r sine theta because that's its definition. Okay, so I get r squared equals 2y, and now I'm also going to sub in for r squared. And we know that r squared equals x squared plus y squared. So I'm going to substitute in for that. So sub in x squared plus y squared for r squared. So I get x squared plus y squared equals 2y. Okay, so I know right away that I have a circle, and I know it is not centered at the center because it does not equal just a constant. It equals 2y. So whenever you have a variable with it, you know that you have to look for or complete the square to find the equation. Okay, so just as a reminder, the equation for a circle is x minus h squared plus y minus k squared equals r squared. All right, so this time around, I'm going to leave y squared alone. I'm going to pull the 2y over. I'm going to leave a spot to complete the square, and I'm going to move x squared to the other side. Now I have to complete the square. So complete the square. So to do that, I take half of 2, which equals 1, and I square it, which equals 1. So what I have here is y squared minus 2y plus 1, creating that perfect square trinomial that's super awesome. And we know that that perfect square trinomial will factor into y minus 1 squared. And I'm going to go ahead and bring the x squared over to the left-hand side just so it looks like an equation that we are familiar with, which is the equation of a circle, not in standard position. Okay, so being that said, I have some information here, and I'm just going to rewrite it so it's a little bit more clear. X squared plus y minus 1 squared equals 1 squared. I know that the center of the circle is h comma k, and I don't have an h this time around, so I have 0 comma 1, that's the center, and the radius equals 1. So I'm ready to go ahead and graph this. Once again, the center is at 0, 1, and the radius is 1. You might want to pause me and go print out a polar coordinate because it's missing out of the notes. So go ahead and grab that, and then you can unpause me and listen to the rest of it to graph it. So remember, the center was 0, 1, and the radius was also 1. So 0, 1 is right here, okay? And the radius is 1, so I'm just going to draw this out. So my circle, and mine looks a little off, is going to be looking like this. I'm trying to make this look better. Okay, so there is my circle that has been placed 1 unit above the center. And that is the graph of that example. Okay, so here's a summary for Objective 1, lines and circles on the polar grid. So let a be a positive real number. Then we can say r equals 2a sine theta. We have a circle with radius a, and the center is at 0, a in a rectangular coordinate. So for instance, if you have r equals 10 sine theta, divide 10 by 2, and you'll know that that radius is centered at 0, 5. Okay? Part B, r equals negative 2a sine theta. So once again, if it was like negative 10, divide negative 10 by 2, and you're going to get a 5. Remember, it's negative. So this results in a center with a radius a at the center, 0, negative a. By the way, do you notice that the y values get affected? Because remember, it's sine, right? Sine goes with y. And then C says r equals 2a cosine theta. Remember, if it was like 10 cosine theta, divide 10 by 2 to get 5. So your center is going to be circled at a, which is 5. And the center is 5, 0. And then r equals negative 2a cosine theta. Let's say that you had r equal negative 14 cosine theta. So take 14 divided by 2. You get negative 7. So the center would be negative 7, 0. So that's what they mean by this. So once again, notice if it's cosine, that a is the first value where the center is. And if it's sine, it's the y value that gets affected. So if you don't want to memorize this, like I said, if you can convert it, and they make you do it anyways, into rectangular coordinates, then you don't have to memorize any of this stuff. So here we go. Here's some more information. If we look at a line, then that formula always in polar is theta equals some value alpha. So theta could be pi over 4. We saw that in an example, pi over 3, etc. A vertical line is going to be r cosine theta equals some value. A horizontal line is r sine theta equals some value. Remember, horizontal goes with y, so r sine theta is y. Vertical goes with x, r cosine theta is x. And also, we went over circles. So if the circle is simply at the center, then your equation in polar is going to be r equals some value. So r equals 5, that means my radius is 5, and voila. If you have moved it in some manner, you get these formulas. So if it gets moved to the right or the left of the pole or the origin on rectangular coordinate system, then we get r equals plus or minus 2a cosine theta. Remember, cosine goes with x. If you moved your circle either above or below the pole, then you get the equation r equals plus or minus 2a sine theta. Okay, and by the way, all these hold as long as whatever value you have is greater than 0. Okay, so with that being said, once again, do you have to memorize this block? No. If you can transform into rectangular coordinates and identify what the graph is, you're fine. However, if you do memorize this, or if you understand it, more importantly, then you can quickly figure out what the graph is without having to do too much work. Okay, so the next objective in this part 2 section we're going to look at is test polar equations for symmetry. There are 3 tests. So we're gonna use this. And by the way, this is kind of like when you were in algebra and you had to graph a line. When you first start graphing a line, you have to plot many points, and then you connect the dots, right? Well, I'm going to take the same approach to graphing stuff in polar coordinates besides lines or circles. But the symmetry tests are going to allow us to quickly determine what the rest of the graph looks like without having to go all the way around the circular plane or the polar coordinate plane. So this will save us some time. It's kind of like when you're plotting lines and you have to plot each point, and then you found out about y equals mx plus b, and you're all happy because it made graphing lines much, much faster. Well, the symmetry test is exactly what that does. So it is like the shortcut. So there's 3 types of symmetry. So let's understand what the symmetries are first, and then we're going to look at the test for symmetry. So the first one is when you are symmetrical about the polar axis. So if you look here, here's my original point. If it's symmetry, or has symmetry about the polar axis, this point is right below in the same position to the polar axis. Now we have symmetry about the y-axis, which is now theta equals pi over 2. And we have this first point here. To get over here, I just have to take and find out, what the value is, so whatever the angle is, and I'm going to subtract that from pi to get that same position, okay? And that makes sense because remember we did the reference angles. So if you're in quadrant 2, you take pi minus whatever the angle is, okay? And then finally, we're going to check for symmetry with points symmetrical with respect to the pole. So here's a pole, and here's my original point. My new point is either one of two things. Either I can say, okay, I can call this negative r theta, because remember, if you take negative r theta, what happens to it? It moves it, right? Or the other option is I can take and call this r comma theta plus pi, because that'll get me 180 degrees away from that point. So those are the three types of symmetry that you can get. Once again, points symmetrical to respect with the polar axis, points symmetrical with respect to the line theta equals pi over 2, and then points symmetrical with respect to the pole itself. So let's check the next page. So the next page says, hey, these are the three symmetries. So if you're checking for respect to the polar axis, you take your original equation and you're going to replace theta with negative theta. Remember we showed that in the first one, so I'm going to highlight that, right? If you want to check for symmetry with respect to the line theta equals pi over 2 or the y-axis, you're going to replace theta with pi minus theta. So that's this, right? And finally, if you want to check for symmetry with respect to the pole or the origin, you have a choice. You can either replace r with negative r or theta with theta plus pi. So if you get, with any of these, if you do what it says and you get an equivalent equation as a result, then the graph is symmetrical with respect to whatever pole you're looking for. So that's how you test to see if you have symmetry. And I do want to point out that you got to be careful because these are nice tests. However, they are not sufficient enough to claim that it is definitely symmetrical. So that's why it's good to plot some points out. Okay? All right, so that's the end of part 2. There is a part 3.